video is here. Okay. So hello, everybody, and welcome to Ryo Suzuki's dissertation defense. I'm just going to introduce the committee briefly in order of distance. I'm assistant professor Daniel Leithinger at the Atlas Institute at CU Boulder and at the Department of Computer Science. And I think in distance, we'll start with Professor Takeo Igarashi from University of Tokyo. And then Professor Hiroshi Ishii from MIT Media Lab. Hello. And I guess I am next, but I already said hi. And then Tom Ye from the University of Colorado, and Mark Gross, also from the University of Colorado.
Good to see a huge crowd here. Thank you for coming.
Very, very nice to see you all. I agree. And so we will have the presentation by Ryo. We aim for about 45 minutes, followed by a question and answer, first by the committee members, and then by the general public, everybody who joined. And then we will go into a separate breakout room and deliberate. And I am very much looking forward to that. So thank you. Mark, have I forgotten anything?
Cheers.
Cheers. All right. Ryo,
okay.
Take it away.
Cool. So thank you for joining us today. I am so excited about it. So my name is Ryo Suzuki. I'm currently 5th year PhD candidate at the University of Colorado, Boulder, Department of Computer Science. Today, I want to talk about dynamic shape construction and transformation with collective elements. So let me again briefly introduce the Thesis Committee. So Daniel Leithinger, who is going to be a chair from University of Colorado, and Mark Gross and Tom Ye are also from University of Colorado. Hiroshi Ishii from MIT Media Lab, and Takeo Igarashi from the University of Tokyo. So let me just start it. So this thesis is about an exploration of the ways to dynamically physicalize the digital information from the computer screen into the real world. So today, the most dominant way to interact with the computer digital world is using graphical display. So the graphical display is dynamic and so powerful, and it can simulate almost anything. But the digital information is trapped onto the 2D flat screen, which we cannot feel, grasp, or manipulate with the hands. So in contrast, this research is trying to explore the ways to dynamically physicalize the digital information out of the computer screen into the real world, so that we can touch, feel, and manipulate through our hands through tangible and embodied interactions. So this research is driven by the vision towards dynamic physical medium with which the user can touch, feel, grasp, and manipulate to think, design, explore, and collaborate. For example, these sketches are from Brett Victor's human representation of the thought at the 2014 WIS keynote. That as he illustrated, the dynamic physical objects and environment can augment and transform the way we think and explore and collaborate. But to achieve this goal, we need to develop two things. The first one is the general purpose method to transform arbitrary digital information into the tangible physical form, just like the interactive physical display. And the second one is we need to develop the interaction model to program and manipulate the dynamic physical object and environment. So to achieve this goal, the first step, this thesis explores dynamic and collective shape construction as a general purpose method to physicalize dynamic digital information. And also, this thesis explores the interaction techniques to program and manipulate dynamic collective elements through direct physical manipulation. So this is why this thesis title is Dynamic Shape Construction and Transformation with the Collective Elements. And this thesis specifically explores how we can make a dynamic shape out of the active or passive collective elements for future of the human community interactions. So in this talk, I want to first describe the background about why I'm taking this approach. And then I'm going to introduce the concept and describe what is the dynamic and collective shape constructions. And then I'm going to introduce my own exploration about the shape construction with the active elements and the shape construction with the passive elements, as well as the interaction technique with the collective elements to program them. And finally, I want to conclude with a discussion about the future research opportunity, as well as the how can we further, develop these kind of collective shape constructions. So let me first describe the background. So we are currently living in between the two worlds. The one is the digital world, and another one is the physical world. So the digital world is dominated by the graphical display, but we are living in a physical world which is surrounded by a rich physical object and environment. So currently, these two worlds are somehow divided each other because the computer cannot really manipulate or control the physical world, and we cannot really leverage the physical object environment to control and manipulate the digital world. But if you look at the history of the human-computer interaction, many research vision trying to seamlessly integrate digital world and the physical world. For example, the Mark Weiser's ubiquitous and calm computing, or Pierre Wellner's the augmented reality, or Hiroshi Ishii's the tangible user interfaces. All of these research vision trying to bring the computation into the real world, so that we can touch and interact with our bodies and embodied interactions. And more recently, the researchers started to investigate dynamic physical user interfaces, such as the shape-changing user interfaces. So in contrast to augmented reality or tangible user interfaces, the shape-changing user interfaces is leverage the dynamic physical object to fully represent the dynamic information in the physical world. So in contrast to using a static physical object to manipulate the virtual object, dynamic physical object can represent dynamic information into the real world. So this shape-changing interface research is inspired by the vision of the Sutherland ultimate display, or Hiroshi Ishii's radical atoms, in which all digital information has a physical manifestation. So driven by this vision, the recent HCI research has started exploring kind of special purpose shape-changing user interfaces, which can only transform into the finite state of the shape. But also, more recently, the HCI researcher also explored the linear purpose shape-changing interfaces, which can be kind of transformed into the arbitrary shapes. So, for example, this is the info from MIT Media Lab, but this is the kind of something like a pixel on the computer screen, but it actually has a kind of physical manifestation with actuated pins. So it does not only show the visual information, but also represent physical information on top of it, so that we could also actuate the existing object on top of the table. So these linear purpose shape-changing interfaces had really promising to represent information, but this system often requires the large mechanically complex devices, which is difficult to deploy into the environment. Because the linear purpose shape-changing user interfaces often require to actuate many elements, so it's become much more kind of complex compared to the special purpose shape-changing interfaces, which makes it difficult to deployable. So one of the interesting challenges and the question is, how can we achieve the both? So in this thesis, I propose the collective shape construction and the transformation as a way to achieve the both general purpose universal shape transformation, but also it can be deployable as well as kind of simple enough for interchangeable elements. So this is the background and the motivation of my own thesis. And then let me just explain about the concept of what is a dynamic and collective shape construction. So as I mentioned, dynamic physical UI user interfaces are often demonstrated through single transformable materials or the monolithic devices which requires many actuated elements. So in contrast, this thesis proposes untitled approaches of the shape changes with the collective elements. Therefore, the focus of this thesis is a dynamic shape made of the discrete collective elements. So the discrete collective elements means the shape that consists of the set of the physical units that are separable from each other. So for example, if you think about a static physical object, then for example, kind of Lego blocks could be kind of discrete collective elements that can construct the shape, as opposed to the 3D printed object, which is consisted by the continuous material, non-discrete materials. But here, this thesis, the focus of this thesis is a dynamic shape made of the dynamic discrete collective elements. And here I argue there are two ways to construct dynamic shapes. The one is using active elements, which is using a self-actuated elements that can move or reconfigure themselves with the internal actuation. Or using the passive collective elements, which is leveraging externally actuated elements that can move or reconfigure through external force or actuations. So this universal shape transformation with the discrete collective elements has been mostly explored in the context of robotics. For example, the self-reconfigure robots or the swarm robots or research in the programmable matter. But in contrast, this thesis investigates the HCI, human-computer interaction aspect of this dynamic and collective shape construction. For example, how can we use it for interactive information display, and how can we use it for tangible user interfaces, and how can we kind of interact with these collective elements. So for this HCI aspect, thinking about this HCI aspect, we need to have a different step of the design exploration compared to the robotics literature. So that's why that's one of my contributions. So for example, when we think about for information display in the robotics, like research like self-reconfigure robots or programmable matter research often assumes the active robotic elements to construct a lattice or voxel-like structure. But one question is, are there any other ways or approaches to construct and represent a physical shape? So to answer this question, I systematically explore a range of the possible representation for dynamic physical shapes. But before just describing this kind of systematic exploration, I just first describe with a metaphor to think about how we can render the information, just like, for example, the Stanford money. For example, in computer graphics, there are many different ways to render and represent information of the original digital data. For example, using a spatially aligned dots with a point cloud, or using a polygon mesh surfaces, or using a voxel representations, or even wireframe connected to each other. So as we can see in computer graphics, there are many different ways to render and represent information. And in the same way, there are also many ways to physically render and represent information with static elements. For example, using Lego blocks for kind of voxel-like representations, or using surfaces like an origami structure, or by bending a connected line can also make physical shape. Also, kind of physical wireframe structure, like using a DOM tool, or using a sliced layer and stacking them together can also make a 3D shape. So these many variety representation can also inspire us how we can physically render and represent information with dynamic collective elements. So to answer this question, I explored 8 possible representations for dynamic and collective shape construction, which is sparse dots and the sparse lines, the pin arrays, and a single line connected line, and boxer representation, and the layer approach, and the surface representation, and Haddon struts. Let me describe each one for briefly. So the sparse dots is to consist of the shape out of the spatially aligned dots, which is mostly commonly used in swarm robots or drone displays. Similarly, the sparse line is the spatially aligned lines to make a contour shape of the 2D or 3D. And the pin array is using extendable actuation to construct the 2.5D shape. The single line is a connected line elements to bend the reconfigure themselves to create a 3D shape. The boxel is using a block-like structure, block-like elements to create the 3D shape. And the layer could be using a transformable seed of the stack of the seeds to make a dynamic shape out of the 3D shape. And the surfaces is using connected elements that can continuously bend together to create a 3D shape. As well as a habit and struts is the connected line, which can extend or the pivot to make a variety of shapes. So one of the contributions of this thesis is to try to explore and identify these variety of rich representations that can be possible with the collective shape or dynamic and collective shape construction. And based on the literature review, I also show a kind of the representation can be missing. So I demonstrate and explore new representation to expand the current scope of the research, as well as I'm gonna also discuss the future research opportunity and exploration strategy to fill the gap for HCI community. So this was a brief description about what is a dynamic and a collective shape construction. So the next, I'd like to explain about my own exploration about shape construction with active elements. So as I said, dynamic and collective shape construction can be achieved either active collective elements as well as the passive collective elements. So first, I'd like to explore what can be the self-active element can construct a dynamic shape. So active collective elements are often used to create a shape in the HCI field, such as GUIs, Swarm, and grid norms. So this recent research called the Swarm user interfaces, which is using the Swarm robots as a display and a tangible user interfaces. So the Swarm user interfaces are mostly represented as shape through the spatially aligned dots, like sparse dots. But what if these Swarm robotic elements can not only represent the shape with the sparse dots, but also through the lines of the pins or connected lines to expand the range of the expression. For example, these Swarm robotic elements can not only move onto the 2D surfaces, but also extend in the horizontally or the vertically to make a sparse line or pin array representation, but also can connect each other to make a connected line to representation that we can grasp it. So I believe this new type of representation can not only improve the expressions of the shape, but also expand a range of application and interaction space by leveraging it. So to explore this idea, we have, so the swarm robots, again, the swarm robots are mostly explored through the collective shape construction. But we are interested in what if we could also leverage the individual shape transformation to make more expressive shapes. So in this paper, in this thesis, we explore the collective and the individual shape transformation through shape-changing swarm robots. And we demonstrated this idea through the shape bots, which is published in WIS 2019. So ShapeBots is a demonstration of the swarm robots that can both individually and collectively transform their shape. So we explore how the shape-changing swarm robots can expand a range of the expression for information display, but also expand application space for tangible user interfaces. So as you can see, the ShapeBot is consisted by the swarm of the robots as well as the extendable actuator. So to this end, we developed a miniature lead actuator that can extend from the 2 centimeter to 20 centimeter. And then by leveraging this modular shape transformation capability, we can make the swarm robots that can not only move onto the 2D surfaces, but also horizontally expand or vertically expand, or even make 2D surfaces with 3D volumetric shape. So by leveraging this capability, we have explored how we can use it for information display, such as extended line for representing a bar graph, 3D bar graph in the real world, or making a contour shape with the collective elements. So this interactive information display can be more expressive and a more richer way to represent information. So for example, this one is the simulation results to compare the swarm robots and the shape-changing swarm robots. And as you can see, the extendable line structure can represent information more expressive way with the same number of the elements compared to the sparse-dot representation of the swarm robots. But not only for interactive information display, but also these robots can enhance the application space by leveraging self-transformation capability. So for example, in this application, these swarm robots can create the vertical pans to not allow the user to touch the hot coffee cup. But once coffee cup is ready to drink, then these robots are gonna disappear so that it can provide a kind of good dynamic physical affordances in an everyday environment. And also by leveraging this capability, these robots can also actuate objects, such as wiping the debris on the desk before the user starts using it, or kind of bringing a tool when the user needs. And also, these robots can dynamically adapt, make an adaptive physical tool to synchronize between virtual world and the physical world. So for example, in this example, the user can synchronize between virtual camp software, or even become an adaptive physical tool that user can use through the rich tangible interactions. So this, the ShapeBot's demonstration of the tabletop scale, the active elements of the dynamic shape construction. But it's also interesting to see what if we can also scale it up for larger scale, such as a room scale. So to explore this idea, we have developed the lift tiles, which is a modular inflatable tiles for active discrete collective elements. So the lift tile is a reconfigurable modular inflatable tiles for room scale shape transformation. So as you can see, these elements are not only the transforming the shape, but also the user can sit down or step in, because it's using pneumatic inflatable actuators that are robust enough to withstand human bodies. it's also pretty extendable from the 20 centimeter to 150 centimeter. So these discrete elements also use a reconfigurable and customizable to align dynamically, so that, for example, the user can reconfigure into the different shape to construct the different configuration, such as 1D shape changing interfaces, or create a 2D surfaces to make a shape changing floor, so that, for example, that can be used for dynamic haptic environments for virtual reality. Or even the user can reconstruct into the different shapes, such as the circle or the horizontal actuation, to make a wall display. So by selectively changing its length, these discrete elements can represent various information as a kind of display, so that it can be used for kind of interactive environments which we can interact with it. So these two projects are mostly demonstration of the dynamic shape construction with active collective elements. And I explored through the shape changes one, dynamic shape made of the shape changes one robots, and also dynamic shape made of the modular inflatable tires. Okay, so next I want to talk about the another exploration about shape construction with the passive elements. Again, the passive collective element means the externally actuated elements that can move or reconfigure through external force or actuation. And the passive collective elements have been also used in the literature, such as the physicalized area assembly or the soft cubes, because it has a unique benefits compared to the active elements, which is first, for example, the scalable, because it doesn't require complex, extensive electromechanical components, as well as it can be possible for higher resolution because the overall size can be small and it can support a large number of elements. And it could also provide a robustness for the structure because it doesn't require the mechanical breakdown of the actuation. But one of the challenges of using passive collective elements is how can we dynamically construct these elements for shape? So for example, consider a robotic arm that assemble passive building blocks, but this process often takes a long time and slow because each robotic arm can only stack and assemble one block by one, which is the serial process. So in contrast, if we can make a parallel assembly process which can assemble and actuate the many collective elements at once, then we can make it faster for dynamic shape construction. So the question is, how can we apply this idea for the collective shape construction of an arbitrary 3D shape? So to explore this idea, we developed the Dynablock, which is a dynamic 3D printing for instant and reconstructible shape formation. So to develop this Dynablock, we take the inspiration from the existing parallel material solidification process of the DLP 3D printer. As you can see, the DLP 3D printer can solidify each layer at once so that it can make it faster to create a 3D shape, as opposed to a serial solidification like IPDM printer. By taking that inspiration from this, we propose the parallel block assembly by using a shape display as the parallel block assembler. So as you can see, we have a shape display and we're gonna have a stack of the blocks on top of it so that each, the shape display can actuate these, the passive blocks but one by one so that we can construct a layer at each time, and by selectively actuating these blocks, we can make an arbitrary 3D shape. So we demonstrate this idea through the Dynablock dynamic 3D printing for parallel block assembly. So as you can see, this is the real time, the video. But as you can see, we can kind of construct the 3D shape in more like a seconds compared to the numbers in 3D printer. So these physical objects are also constructed with the passive collective discrete element so that we can deconstruct and deconstruct over and again. And this is also using a layer-by-layer assembly by selectively actuating pins so that we can make an arbitrary 3D shape just like a 3D printer. So given if we can make it more dynamic and interactive, then we can, for example, dynamically physicalize information and shape out of the graphical display so that we can tangibly interact with it, as well as seamlessly synchronize between digital world and the physical world. So the Dynablock could be one of the steps toward this kind of vision to make the more dynamic physicalization between virtual world and physical world. So dynamic shape construction with the passive collective elements is demonstrated through the Dynablock, which is a parallel actuation of the for voxel representation. But I have also explored the different ways of the parallel actuation for example, the sparse dot representation by using electromagnetic coil arrays to externally actuate a swarm of the magnetic markers. So using a PCB-based electromagnetic force to continuously actuate these passive magnets to make, for example, using for the shape with a sparse dot representation, which can dynamically move with user's interaction. So and also I have explored the parallel actuation of the passive existing object for spatial reconfiguration. So in contrast to using a custom built passive elements, we could also actuate the existing non-custom made objects such as furniture, the chair, and the desk, so that these robots can move and reconfigure the entire space dynamically, because it's using a collective actuation of the swarm robots so that it can dynamically reconfigure the space. So again, the dynamic shape construction with the passive collective elements are demonstrated through these passive Dynablock, Reactor, and RoomSeed projects. So these are my own exploration about the shape construction with the passive collective elements. And then I'm gonna finally describe what could be the interaction technique with the collective elements. So far, the projects that I described was using dynamic collective elements as more like for information display or a tool to interact with it. But the collective elements could be more than just a tool or information display, but also a medium to create or animate through exploration, like a clay or building blocks. So one question is, how can we use these collective elements as a dynamic medium to create and explore dynamic motion? Because in contrast to static Lego blocks or Lego blocks of clay, these collective elements can dynamically actually move. So how can we use it as a dynamic medium to explore the dynamic motion? And what would be the interaction model look like? So the construct, these dynamic motions often require the programming. But in the existing system, the interaction with these collective elements happen in the real world. But the programming often happens on a computer screen. So we cannot really program and explore this dynamic motion within the real world. So the goal of this project is to answer this question about how can we enable the end user to create and explore dynamic motion, not through coding on a computer screen, but through direct physical manipulation in the real world. So for example, we propose a way to create a shape through the sketching or the defining a variable of these shapes to propagate the change between the parameter. So this interaction technique enable us to program and explore this dynamic motion not only through the coding on the computer screen, but also but through the tangible interaction within the real world. So one of the inspiration to so that's why we to demonstrate this idea, we have explored the React, which is an interactive Swarm UI programming. So one of the inspiration to make this the direction manipulation is the constraint-based programming. So the constraint-based programming is using the three-step, which is the first define a variable to parameterize the word, and then you bind these two parameters together so that the object and graphics can responsibly interact with it. So these techniques are particularly powerful because we can really make dynamic motion through the interactively interact within the real world. So we have explored how we can also use this technique to the Swarm UI programming. So to make that happen, there are three steps. The first one is a user can create a static shape with the sketching so that the user can interactively create a shape that the user wants to make it dynamic. And user can also define a parameter to demonstrate it, which can be later to use it as a dynamic variable of the shape. And then we can bind two parameters together to make this shape dynamic. For example, in this case, the binding the width of the rectangle can be bound to the position of the element, so that if you move the points, then you can actually dynamically move these elements. So we can use this dynamic interactive programming for the dynamic data physicalization, data visualization. But also we could use it for interactive simulation of playing the game, to playing and making the game through the tangible interactions. Okay, so this was the last section of my own exploration. And for the last, I want to discuss the future research opportunity as well as what could be the design implication of this my own exploration. So for discussion and the design implication, I want to talk about three things. The first one is for active collective elements, how can we combine individual transformation as the building blocks or to expand the various representation? The second one is about passive collective elements, which is how can we combine the both active and passive elements to construct the dynamic shape? And the third one is a collective actuation, which is how can we leverage the multiple active elements to collectively actuate the passive materials. Let me first describe about active collective elements. So as I showed, if we can combine the transformation building blocks, then we can not only represent the shape not through the sparse dots, but also the sparse line or the pin arrays, which is the showcased through the shape bots. But this design exploration strategy is not only available for shape bots, but we can also combine these building blocks, transformation building blocks, to explore more different way of the representing information. So as we can see, these building blocks is not only the horizontal movement or vertical extension, but also the bending, the climbing, the connecting, transforming, and spacing to change individual shapes. So by combining these transformation building blocks, for example, by using horizontal movements as well as the connection, we could potentially use the distributed swarm robots that can create a dynamic graspable shape so that we can interact with it. But once it's done, then it's going to be disconnected and distributed to the sparse dots. And also, we could combine the vertical extension as well as the bending capability to create a different way of representing information through the pin display, which can be used for the bending lines. Or even using a horizontal extension as well as the bending to create a connected line-based representation similar to the chain form or the line form. But each element can also extend and scale it up, which allows us more expressive information display as shape terms, as well as the interactions. And also using transformable layers to transform a space between it to make a 3D shape. So as I demonstrated, these transformation building blocks can be used to combine to start exploring more various representation for the future work. The second one is about the passive collective elements, which is how can we combine the both active and passive elements to construct the dynamic shape. Again, in my own work, I demonstrated these passive collective elements through the Dynablock and the room shift. And as you can see, the dynamic shape construction is combined through the active and passive element to create a dynamic shape. But this the example, that's only the one example, and we could also expand this exploration strategy for many different ways. So, for example, what if the swarm of the robots that crawl on a passive kind of tube-like materials, and then they can selectively bend and crawl together, so that the swarm of robots can construct construct the shape out of the passive materials, or using like a timber-like structure as well as the swarm robots that can pivot it and rotate it and connect it, so that we can dynamically construct these happiness structure representation with not only for active elements but also combining with the passive elements. So as I said, there is a rich design space of this representation. And in this thesis, I demonstrated and contributed through this exploration. But by expanding this exploration strategy for many different ways, we can start exploring new domains and start filling this gap for future work. So the third one is the collective actuation, which is how can we leverage the multiple active elements to collectively actuate passive materials. So again, in my own work, I demonstrated this collective actuation through the room shift. And the room shift is leveraging the individual or the collective or simultaneous movements of this static furniture. But again, these are just only the one example of the collective actuation. And we can think of the many different ways of the design space of this collective actuation, such as enclosing the static objects, or the tumbling the static objects, or the connecting the static object together, or extending, or the stretching, or compressing, or the shrinking these transformable passive materials, as well as the rotating and the pivoting these objects, or the swinging, shaking, arranging, assembling, or disassembling to interact with the passive object to create a shape or provide affordances. So, for example, these are my own just random exploration about how can this swarm of the robots can compress the passive materials or extend and stretch these objects or the enclose to make a shape. And it's also somehow interesting to see, to leverage these swarm robots and magnetic actuation as a prototyping environment for the shape-changing user interfaces. Because actuating these shape-changing user interfaces, they're very expressive, so that we can kind of create different shapes to start exploring it. And also, it's interesting to see if we can transform the larger object like a transformable furniture, so that these are swarm of the robots that can actuate and transform the furniture to collectively actuate it together. So the if this swarm of the robots can also, seamlessly blend and integrate into the real world environment, then these swarm robots can also activate and actuate existing environment more different ways. So this could be also the future work that can for many possible applications. So in this talk, I have described about the background of why I'm taking the shape construction with the collective elements, and I introduced the concept of what is dynamic and collective shape construction. And then I have described my own exploration of the shape construction with the active elements through the shape-changing swarm robots, as well as the modular inflatable tiles. And I described the shape construction with the passive elements, which is demonstrated through dynamic box assembly, actuated swarm markers, and swarm robotic actuation. And I also described how we can interact with these collective elements to program dynamic motion to explore it. And finally, I have showed the mission, the design space, as well as exploration strategy to further fill the gap, as well as how can we use both passive and active elements to construct and actuate environments and passive objects. So before closing my talk, I just want to thank all of my advisors in the Thesis Committee, as well as I want to thank all of my collaborators here. And I also want to thank all of the friends and the family and Koto and Tomomi for my continuous support during my PhD. It was not possible without the help of these people, so I really thank them from the bottom of my heart. So this is the end of the talk. So thank you again for joining us today, and I'm happy to take any questions.
Who's the chairman? Can I go? Can I ask a question?
So yes, I think what we will do is go with questions from the committee first, for all the committee members, and then we will open it up to everybody else.
I see. But from distance point of view, Professor Igarashi may have priorities over anybody else.
Oh, that is correct.
Yeah, I follow your order.
Okay, so I'll open it up to Professor Igarashi first then.
Yeah.
Well, not much, but I want you to clarify a little bit more the difference relation with swarm plots. So you only said, your difference from swarm robotics field research is you focus HCI, but I want to hear a little bit more. Mainly, what are the main applications they discussed, and what kind of interaction they propose in robotics field in swarm robots? Can you clarify?
Yeah, let me just bring it up. Yeah, maybe this. So the Takeo's question is this universal shape transformation of the swarm robots are mostly explored in the robotic literature, and what could be the difference, major difference, or what could be the previous exploration in the robotics field. So I want to first describe about the application of the robotics, which is mostly for the space exploration, because the collective elements are interchangeable, so that instead of using the one big robots, it can be more robust and distributed ways to do it, as well as the research and rescue. So I found the most of these self-reconfigure robots, the swarm robotics, robots in the robotic literature is mostly not focusing on the human aspects of the interaction. So so I think that's the biggest differences in terms of how can we use it, because also one of the major difference in terms of the design aspect is this the self-reconfigure robots or swarm robots. The focus of these self-reconfigure robots or swarm robots are more focusing on universal shape transformation aspect, as opposed to the dynamicity or the speed of the transformation. So, for example, this is a kilobot. The kilobot can transform into arbitrary kind of 2D shape, but the transformation from the one shape to another shape often takes minutes to create a shape. So it can be kind of pretty hard to use as an interactive system. On the other hand, my own exploration of focuses on how can we make it more dynamic so that it can be more interactive, not only for information display, but it can be interactive between the human and the robots. So to answer your question, I think there are two ways of the differences. One is application domains, which is more focusing on the interaction aspect between the human and robots, as opposed to rescue or the space exploration. And the second one is the using it for HCI aspect. It needs to be more dynamic and interactive, which can transform in more the second instead of minutes and hours. So these are major difference, I think.
Okay, thank you. Yeah, I may come back later, but I think it's better to go on. Thank you.
Maybe I can follow up on that. I would like you to explain when you use the word more dynamic. How do you measure dynamic? What does it mean by more dynamic? What kind of heuristic dimension you use when you have A and B? Why is A more dynamic than the others than B?
Yeah, that's a good point. I didn't have so the formal definition of the dynamic. It's more like a relative terms about the kind of shape transformation. So, but in my thesis, so here I didn't intentionally explain about the terminology of the dynamic and inert, which is introduced in my thesis. But in my thesis, I defined the dynamic as the which can change their own property through internal or external actuation, as opposed to inert is the which cannot change the shape, which cannot change the property. But I think the Tom's question is more like how fast can be dynamic and how fast can be static. So I do think there is no universal measurement about dynamic. For example, it can also depend on the application. So to answer that question, I use as more relative terms to describe it.
Hiroshi, I think distance-wise, you'll go next.
I'm from Cambridge, Massachusetts. First of all, it's nice having a party. I see so many familiar faces, Kai gangs, also the academic colleagues all together. Listen to Ryo Suzuki's very impressive talk. First of all, I'd like to say congratulations. This is really great contribution. Maybe the most important thing is conceptual layer, pushing the envelope to the next levels. Of course, technically, your demonstration is very solid, very clever, and very creative. Also, application is interesting, something very funny. But the most important thing is you are making people ask a question. What would be possible if you could program the real physical world computationally? This is a fundamental question, open the eyes of the people so that many people like Ivan Sutherland, ultimate displays, and programs matters, radical atoms, but you definitely push envelope to the next level, showing so many interesting variation and raising the questions. So maybe technically, it may not scale up. Moore's law is not applicable. We know very well. Many reconfigured self-robots stop working. Also, perfect modular like a library is impossible because we can't foresee the futures. But I think a conceptual intellectual contribution is quite strong. So I'm very, very impressed. The one question, actually I have 10 questions, but I ask only one question. And if this is a human material interactions, you are sitting on the chair. You trust chair does not betray you by changing a form all of a sudden or disappear. So persistency of the physical world is fundamental ground you can believe, count on, because cognitive models. And also when my group studied radical atoms, most difficult question is affordance. How to communicate to the people who cannot really infer what kind of the shape changing may happen. You know, you as a God programmer, but I didn't see clear clue how to communicate user what is a extension that the robot can make it. Otherwise, it's very scary. So maybe psychologically, from a cognitive point of view, how can you be responsible to communicate the users? Don't scare people, but also develop the new trust. Because the departure to persistent, frozen physical world make a huge challenge. And I don't know the answer to this question. I've been thinking for more than 10 years, but still I don't know the answer. But you're a PhD, so I think I want to hear your comments.
Wow, that's that's a really good question as well.
Of course.
I have also been thinking for a while. Oh, so the question is, so how can we? So these are more like a dynamic physical environments, so that it can suddenly change the environment. So for example, this robot can suddenly change the environment. Like if you want to start trying to sit down on the chair, then this robot can potentially move the chair from you so that it hurts you. So this is a this is the fundamental the design things of the when we need to make the shape-changing user interfaces. So let me think. So one of the way. So this is a more like more like the kind of direct way to answer this question, but it would be somehow interesting to explore more, not as rigid materials, but more leveraging the soft materials which can easier to integrate within the real world. So for example, this modular inflatable tiles, using a pneumatic actuator that can relatively, relatively kind of how to say, that it doesn't hurt when the contact to the people. So I haven't explicitly explored so I have mostly explored in the rigid materials, but as I also want to share, it's also possible to explore the soft materials, using soft materials. So one of the challenges of using soft material is it often requires the bulky actuation system, so that it needs to be more, these are kind of technical challenges to make more the smaller as well as the sum of the elements to make it. And as Hiroshi also mentioned, providing affordances are particularly important ways to communicate between the people. So in fact, actually, like the affordances are also demonstrated through the kind of creating a shape or creating a shape. So these or the using the movements to interact, using the movements to communicate with the people to show what they are trying to move or something like that. So again, I think these are more like, you know, the temporal solution maybe, but I have been thinking that one is using more the soft materials as well as more thinking about the affordances to provide, to communicate with it.
Great, thank you very much. I think there's three things for the radical terms. Transform, you made a transformation. Also conform, you as engineers, you can really control the way material transform. But how to inform people is still a big question. Making soft materials is not the real solution. It's very ad hoc way because you trust chair to sit on. Physical world, floor, stay still. But you are changing the fundamental laws of physics or perception. So this might be a very big challenge, how to really change the cognition, how to make people really understand, appreciate, rather than scare, for example, or get hurt, because chair doesn't move, table also doesn't move. All of a sudden, it move. That's usually make people very scared. So I think this might be a really good challenge to discuss in the last chapter of the PhD thesis for the next generation of the researchers. That's my suggestion. Thank you.
That's so, yeah, that's so nice suggestion. Thank you.
So just related to that, excuse me, related to that question that Hiroshi just asked, I also wonder what your thoughts are when you're talking about the interaction with the collective elements. You mainly focused on constraint-based programming, and I wonder about your thoughts on the level of autonomy that is required when you interact with a swarm. So what do you think are the implications of different forms of artificial intelligence to coordinate between a swarm, and how do you communicate that to the human operator in the end? And can you talk a little bit about how you used kind of autonomy in your projects, because it varies, right, between say room shift and lift tiles, for instance.
Right. So again, this thesis mostly focus on the how to say the shape construction transformation aspect of this shape, because you know it hasn't been explored in the literature. But as Daniel said, it's also important aspect of how we can interact with these collective elements. So again, this most of my work is mostly kind of pre-programmed by the developer, and then it assumes somehow kind of the developers the finite set of the interactions that can be supported. But so again, my thesis doesn't explicitly explore these interaction aspects, but that I also want to point out the related work also start exploring what could be the potential interaction with these swarm robots. So, for example, this one is from the Stanford shape lab, but they start exploring about what could be the natural interaction between human and swarm robots, and they use the study about mock-up study about how user can use it, how user can communicate through the gesture or the voice or the kind of interaction. So again, I think there are many rich design space and rich opportunity to further explore these the interaction through the gesture of the through interaction. So I just want to point out this literature or the related work to as a kind of hint to start exploring it. But I also think even in terms of the programming aspect, we can also explore more in different ways, such as how can we combine the blocks together to start changing their property, so which also allows us more kind of dynamic, tangible interaction to manipulate and control. As well as I'd like to talk about the kind of human in the loop or autonomous application of the swarm construction. So these are also more like, how there is a still interesting research question about how which part the human involved, and which part the human, which part the robots involved. So, for example, one of the application of these swarm robots construct some kind of static elements, but it's also somehow interesting to explore the human in the loop application. So, to go back to Daniel's question, we have also explored some of the different ways to interact with these swarm robots. So, for example, in the room shift, what if the user bring a table, bring the seat of the table, so that they can define where the table should be, or we have also explored how can we kind of communicate or interact with this robot through augmented reality, so that these robots, so we can see the intention of this robot through augmented reality. So to answer the question, my thesis mostly focuses on the technical shape construction aspect, and we haven't explicitly investigate the overall interaction paradigm of these collective elements. But I want to point out some of the literature, some of the related work to start exploring this aspect. And I do think it's also, it's more like a future research opportunity. Yeah.
I think, Mark, you might be next.
Oh, hi, everybody. It really is really great to see all these colleagues and friends. Hi, Mike. Great work. You know I'm a fan. I'm so impressed by the range of work that you've done. And so my question, and I am obliged to ask a question because I'm on the committee, but I'm really more interested in hearing what other people, all the cool kids in the room, have to say, so we can keep this brief. Your work spans the range from centimeters, millimeters at the reactile to meters at the room shift. And I wonder if you could comment on what problems need to be solved when this thing scales down or up. So when you have sort of 10 to the minus 6 robot unit elements, or 10 to the 6 elements. Right now, you're sort of dealing with 10 to the 1 to 10 to the 2 elements. What problems do people need to solve in order to work with large numbers and small sizes?
Yeah, that's really good question. So one of the challenges, particularly for, so I just want to point out this figure, which is my favorite, but this is the figure from the Zuis by Lugok. But this illustrates how the size of each element can be smaller to the more like a stuff instead of things. So currently we have more like a centimeter scale, like a Dynablock or the shape plots, the centimeter scale. So which is more like in between objects and a particle. But as Mark said, if this element can be smaller and smaller and smaller, then it's gonna become a particle and atoms. It can be distinguishable between atoms. So again, this is a somehow very interesting continuum, and obviously there is many technical challenges to do that. So one of the first of all, it depends on whether we want to pursue the active elements, just like swarm robots, or the passive elements, which is the external actuation. So I want to describe more like active elements because it's more like a swarm robots. So for the active elements, I think some of the potential, the technical limitation is one is actuation, which is mainly the motor. Another one is like a battery. So because these two are the main components which requires a large space. So for the motor, I had a kind of the review, which is kind of the Muir law, which not a drastic the Muir law, but it's the size of each motor is a continuous integration. So it's could be possible to make the millimeter scale the swarm robots within maybe in a decade. But this is probably one of the expectations I think. Another technical challenges would be more like a battery. So currently my robot has their own LiPo batteries, but it can. I also point out some of the works that start exploring like the wireless power transformation to make a much more smaller. So this is the one of the technical, the hints that we can miniaturize to do that. So again, actuation and power could be one of the major challenges, and one of the way of this could be kind of offload into the environment. So the power could be offload into the environment because we are seeing the wireless power transformation for this. Another one could be also the using offloading actuation into the environment. So for example, these are as I said, it's the same similar to my reactor, but they are using the magnetic actuation to actuate this a centimeter of the millimeter scale size of the shape, or this is using the vibration of some to actuate this kind of static elements. So I think it's also interesting the consideration of which aspects should be offloaded into the environment so that we can make it smaller. So this kind of strategy, I took this kind of strategy to miniaturize for the Dynablock the reactor, and then there should be some way to offload some of the component, as I said, like a battery or actuation to do it. So in terms of the short-term goal, like 10, 20, 30 years, I think this a combination of offloading some of the major components into the environment could be one of the practical solutions to do that. But for like a longer time, like 50 years and 100 years, maybe there might be some completely drastic, the change from the molecular biology or like, yeah. So I cannot expect, I cannot really answer for the long term. But for the short term, I'd say the technical challenges, particularly the technical challenges, could be the actuation as well as the battery. And to further miniaturize it, I think the offloading this actuation power into the environment could be one of the promising way to achieve it.
Oh, Daniel, microphone.
Thank you very much, Ryo. I would just like to open this up, this question and answer, to the general audience. Just as a note, we'll be heading to a separate breakout room in about 15 minutes. And so also we would like to extend to other faculty members who are present. I see quite a few that have joined. You can join us in the breakout room as faculty in the continuing discussion. So that's in about 15 minutes, but let's open it up to other questions. And if you would like, you can also type your question. I'm happy to read it out.
Cool. Wait, can you break down? Should I? Or
May I ask a question? Actually.
yeah, for sure.
Hello, everyone. This came from MIT Media Lab. Congrats, Ryo. Impressive work as always. I had a question about. So I liked how you end up with this proposing different configuration to show, really big space. So which implies there are 10 more papers that can come out from this framework. But I think but I was also thinking how you started your presentation was thinking of what's the specific purpose device versus generic purpose, where generic purpose is about one device that can do lots of different stuff. But now you are showing the dimensions. Yes, each of them can do lots of different stuff, but each of them have a very specific capability in terms of shapes you can make, interaction you can make.
Mm-hmm.
I was thinking where you are heading towards. Are you saying these are different design options you can have, but each can be used for very specific purpose? Or are you envisioning there will be a master collective module that can do everything, that can do all of this, and that becomes the generic device? But yeah, I wanted to hear about this relationship of generic and specific after this. Yeah, design space.
So yeah, so for me, these are more like the aiming towards the general purpose shape transformation. So using a collective elements is the way to not limit into the one or the at most multiple shape transformation. But I was originally aiming for the shape transformation into the arbitrary 3D shapes. So I do think it's theoretically possible because we can see this kind of the different representation can also make the arbitrary different, more like a universal shape transformation. But in the reality, I really understand because it's a very different from the theoretical point of view, which is which is more like a, just focusing, just transform more like a finite set of the elements. So I just want to point out this kind of impression comes from the theoretical point of view, the practical point of view. So I actually tried to also create. So I do think one of the universal shape transformation could be the dynamic block, and I have also tried to explore the dynamic universal shape transformation with Habermas struts and the layer approach. But in reality, it was really hard, so we really couldn't do it. So that was a kind of how to say it's always limited by the technical aspect in contrast to the theoretical aspect. But I think the using collective elements could be theoretically transformed into the general shape. So I use the special purpose or the general purpose is the more like how many shapes the one object can transform into. So for example, if the shape-changing user interface can transform into the one or two or three different shapes, then I'm thinking these are more like a special purpose. If these elements can more like many, how to say, arbitrary the shape, then I'm thinking it more like a general purpose. So it's somehow I should probably explicitly mention that, but it's somehow different from what types of application can be supported. So the special purpose doesn't, I didn't say the special purpose as just only for one application, but it's more like a kind of how many states they can transform into. So it's probably makes you a little bit confusing, but but I do think in terms of application, we can also think about the different dimension or the different categorization of the classifying these approaches. But this kind of, so to answer the question, my intention of the special purpose or the general purpose is the number of the transformation can be possible. And then from the beginning, I think these using collective elements can theoretically transform into the different shape. But in reality, it's sometimes very difficult, so that it somehow feels like a very special purpose. So it's kind of limitation in terms of theory or in terms of practical. But yeah, so that's my honest answer.
Thank you.